Greetings, folks. I just had the strangest conversation. A parent called me and said that she'd heard that there was a test coming up and that she demanded that I make the test easy. And I said, I'm not going to go out of my way to make it, particularly hard, but I still have to test to see whether the students really understand, what the material is about. And so I'm going to have to, beg off from the request. And she said, if you don't do it, you're going to be sorry. And I said, oh, yeah? And she said, yeah, I'm into voodoo. And if you don't do it, I'm going to hex you. Now, being the cocky soul that I am, I said, bring it on. Be interesting to see how it works out. Anyway, this video is designed to deal with the idea of centripetal acceleration. If you remember in class, we were looking at situations where a body was moving on a circular path. We decided that there had to be some kind of naturally existing force in the system that was forcing the body out of straight line motion, and that there was going to be an acceleration in the system that was center seeking, that was centripetal, whose magnitude was equal to the magnitude of the velocity squared divided by the radius of the arc upon which the body was moving. And I just gave you that information during class without justification. I said that later on down the line I would prove that that was true. This video is designed to show you that in fact it's true. So anyway, that's what we're about to do. And I'm hoping that nothing unpleasant comes of this altercation I've had with the parent. We'll just have to see how things work out. This is the most general definition of instantaneous acceleration. Essentially what you're doing here is you're looking to see what the change in the velocity is as a vector over some time interval, and you're taking the ratio of the change in velocity per unit time. This quantity right here gives you what the average acceleration is over the time interval. If you then let the time interval become very, very small, which is what this part of the relationship basically is identifying, then you're zeroing in on what the change in velocity with time is at an instant. That's what the instantaneous acceleration is. So if we're trying to derive an acceleration for centripetal, for center-seeking forces, what we're trying to do is to figure out how the velocity changes in the center-seeking direction per unit time as delta t goes to 0. To do that, we need two things. First thing is we have to figure out how delta v is related to the geometry of the motion as the body is following through this curved path. And the second thing is we need to find out whether or not delta v, the direction of this change in velocity, is really toward the center of the arc that the body is moving on. So here we have the situation. The body is right here at point in time 1. It's got a velocity vector of v1. It's r units away from the center of the arc. It proceeds along here over a time delta t. At the end of the time interval, it's at this point. It's got a different velocity, same velocity magnitude, but the direction of the velocity is different, so it's basically a different velocity vector. Again, it's r units away from the center of the arc. There are a couple of distances that are kind of important here. The first is the distance that the body physically travels, which is the arc length. And the arc length is equal to the magnitude of the velocity times the time during which it traveled. It's v delta t. And the second distance is the secant, which essentially is the distance, the actual line of sight distance between event 1 and event 2. What's interesting to note is that as delta t gets smaller and theta gets smaller, the arc length, s, and d approaches one another. They become basically one. So when delta t is really, really, really tiny, essentially d equals v delta t. This is a fact that we're going to have to use as a substitution down the line in the derivation. While we have this sketch, there's another observation that's kind of important. When delta t gets really, really tiny, which means theta gets really, really tiny, v1 is going to look like so, and v2 is going to look like so, and delta v is going to be the vector difference between those two. And if we do graphical vector subtraction between these two, we take the first vector, v2, and I've made it bigger here just so you can see it. We take v1 and we take minus v1, so it's going to be a vector that's got the same magnitude but opposite the direction. And we put the head to tail like so, and we draw it out. And then to figure out what v2 minus v1 is, we go from where we started to where we end, and that's what delta v is. And the interesting point here is that apparently the delta v vector is in this direction, which is the center-seeking direction, which is the direction that we need to have it be if, in fact, the acceleration that we're going to come up with is going to end up being centripetal. So we've just taken care of one of the two things that we had to get done for this derivation to make sense, and that is that this delta v is centripetal, center-seeking. So back to the original sort of setup where here's event 1 and here's event 2 and there's this big time interval between here and here. If you look at the geometry of this thing, you've got these two radii, you've got the secant across here, which is producing this isosceles triangle. It's got an angle theta, which we know, or we would assume we know. This is a right angle between r and v1, and this is a right angle between r and v2, which means that if we take the vector difference between v1 and v2, here's v1 or v2, here's minus v1, here's the vector difference. This triangle is also going to be isosceles. This magnitude and this magnitude is the same, and in fact this triangle and this triangle are going to be similar. And because they're similar, it means that if you take the ratio of any two sides in the triangle, it will equal the ratio of the same two sides in the other triangle. In other words, the ratio of the non-equal side to one of the equal sides equals the ratio of the non-equal side to one of the equal signs, or d over r is going to equal delta v over v. So now we're ready to put all the math together. So this is just sort of a reiteration of what it looks like as far as the path goes, where d and s become 1, which means d is the same as v delta t. So I've got, here is that ratio that we just came up with because of the similar triangles. For d, I'm going to substitute s, which in turn becomes v delta t. The delta v over v just trails along, the r just trails along. We get down to this relationship right here, and with this I can bring the delta t down and I can bring the v up, and I end up with delta v over delta t equals v squared over r. But because this situation, the way we've set it up, this is only true in the limit as delta t goes to 0, which is to say when theta is really, really tiny. We should really write that relationship in the more formal sense of, in the limit as delta t goes to 0, delta v over delta t equals v squared over r. This quantity is the definition of an instantaneous acceleration, and in fact, because we've already figured out that delta v is center-seeking, we're talking about the centripetal acceleration. Consequentially, a centripetal equals v squared over r, and that's your derivation.